Here in the upper Midwest, I know we're more concerned about the weather. I know we talk more about the weather than maybe any other group of people in the country. And I think maybe we should have a basis for concern being here in the top of the Mississippi Valley. But to carry on our tradition of talking about the weather, we've come over to the University of Minnesota to the physics department to have some serious discussion about the weather with Dr. George Freier, talking today about how the weather affects us, concerning temperature, humidity, frontal systems, and air pressure, or the barometric pressure. That's always one of the important readings that we have, along with the temperature and the humidity on our 10 o'clock news. Well, Dr. Freier, maybe you could tell us a little more about air pressure and how it affects the weather.
All right. I always think that a good way to learn something about something is to do a demonstration,
Right.
a little experiment.
Right.
The air pressure in the atmosphere, as anything experiences it, is due to the fact that there are molecules hitting the surface and bouncing off, changing their motion. There are many molecules, they all change their motion, and it's of such a magnitude that on 1 square inch of this can, for instance, there's very close to 15 pounds force. Now, when the can's just sitting here like this, there's that force on this side, there's air molecules inside, so they're hitting on both sides of it. So for our first demonstration, let's just get a little feeling about how large this 15 pounds force per square inch is, and we can do that by removing the air now on the inside of the can. I have a little vacuum pump here, and so let's just turn the vacuum pump on and see what happens to our can.
You can hear it.
Yeah, gets crippled.
And there she goes.
And I think you'll kind of appreciate the force that is. Now,
Yeah.
of course, we are all subject to exactly that same thing, but like the...
Well, it's very impressive. I guess I'm surprised at how quickly the can collapsed, and I suppose it could happen to a person's body if you could somehow take away the air pressure that we have on the inside of us. But we usually don't talk about collapsing cans. We think in terms of a barometer that we have on the wall at home, and usually think about pressure in inches of mercury, don't we, Doctor?
Mm-hmm, that's right. And it's quite simple to make a barometer, a device which we call a barometer. In this case, I'll make you a mercury barometer,
All right.
one of the earlier ways of measuring air pressure. And if you'll inspect this tube here, notice that it's open on this end. It's just like a big test tube closed on this end.
Yeah.
And for convenience, I've set this up. I've got an identical tube here that's been filled with mercury, which is a liquid. Now, let me do the following thing with this tube. I will put my finger over here.
Little mercury spilled out.
And so that no mercury will run out, and I'll tip the tube upside down and immerse it in this tank of mercury. And you see the mercury still at the top there
Yes,
yet.
yes.
But now I let go with my finger, and we notice that it's dropped in here. All right, there's nothing taking the place of the mercury in the top of the tube here now. That's essentially a vacuum up there. So the pressure, the atmospheric pressure pushing down on the dish here is essentially balanced by this column of mercury that we have right here. And this mercury is so heavy, this is equivalent to about 32 feet of water. But if we take the ruler here now, and if I measure from this surface up to here, we find that the pressure today, well, I've got just about 29 inches. Or if we wanted to do it in the metric system, we could flip it over, and it's about 740 millimeters of mercury, or 74 centimeters of mercury.
So that really is a measure of the air pressure.
And this then is a measure of the air pressure, yes. That is, this mercury is so heavy, you might just try lifting that dish a little bit to appreciate how heavy the mercury is. And
It's hard to move.
Yeah, and this column here of mercury is equivalent to about, as I said before, to about 32 feet of water. If I did this with water, I'd have to have the column 32 feet high. 32 feet high.
We just hold that up there, and so you can see the column of mercury a little bit better. Well, now let's do a little talking about humidity, relative humidity, and a relative is really the key word here, isn't it?
Right.
Talking about humidity. Now, what demonstration do you have for us now?
Well, I've worked a problem kind of backwards here just to get the idea to us. I've considered a room which is about a little over 10 feet by 10 feet by 10 feet, which might be about a good-sized bathroom.
Yes.
And let's imagine that that room was perfectly dry to begin with. And I first of all set this larger flask in here, which has got 1,000 cubic centimeters of water in it. If I set that in the room, and if the room were at 86 degrees Fahrenheit, that is, all of this water would evaporate, every bit of it. And then if any more tried to evaporate, it would condense as fast as it would evaporate. We'd say that the air is saturated at that temperature. And I would then say, since it's saturated, it's 100% relative humidity.
So really the air in that room would absorb that much moisture.
It would
at
take that much
temperature.
moisture, yes. It would be as a gas in the room at that temperature. Now, if we cool the bathroom down to 68 degrees, let's cool it down to 68 degrees. This time, and let's start with a perfectly dry room again, and if I let this water evaporate, I would find that there's only this much water would evaporate. Instead of 1,000 cc's, which we have here, it's down to 570 cc's here. And at that temperature now, the molecules are traveling slower. It's harder for them to get away from the water, and it's easier for them to get trapped by the water. And so the equilibrium is when we have about 570 cc's of water in the air. So and that would be 100% humidity at that temperature.
That temperature, yes.
And then if I cool the room down to 50 degrees, started with a perfectly dry room, evaporated all of the water, and I would find only this much. It's about 305 cubic centimeters of water evaporating into the room. So we have varying amounts of water here, which depend very much on the temperature of the room.
It's a little bit cool for a bathroom.
Oh, yes, yeah, that's a cold bathroom, and this is a hot bathroom,
Yes,
but
yeah.
nevertheless, it kind of shows the relative
Certainly.
amounts here very well. Now, let's just look at this one more way yet before we go on. Let's keep the bathroom now at the high temperature of 86 degrees.
Same temperature.
The high temperature one now. Now, if that air in the bathroom held this much water at that temperature, remember here it was saturated, it was 100% humidity. Here it would be 55% humidity.
Yes.
If it had that much water, and if it had this much water, it'd be 28% relative humidity.
So
See?
that's a dry, cool bathroom.
That's a dry. Well, no, it's a dry, hot bathroom. It's a wet, cold bathroom. Is that about it?
That's relative humidity.
Yeah.
As we're getting closer and closer to a full use of the metric system, Dr. Freier has devised a handy reference guide here for conversion. I suppose one of these days we won't be converting probably from Fahrenheit to Celsius, but a handy way to remember from one system to the other, Doctor.
Right, yeah. The United States is kind of alone on this Fahrenheit
Yes.
degree system over here yet. But I always think it's useful to have some temperature that you're real familiar with, like the temperature of your house. And if you remember that 68 degrees Fahrenheit is equal to 20 degrees Celsius, then we can work both ways from that point. And all you have to remember then is that for every 9 degrees on the Fahrenheit scale, you have 5 degrees on the Celsius scale. So you just match those two up there, or if I go 9 up here, 68 plus 9 is 77, I go up 5 on this one. So you can kind of keep track of the two temperatures. You had a little rule too.
Well, the two that I remember, you just reverse them. 61 degrees Fahrenheit is 16 degrees Celsius, and 82 degrees Fahrenheit is 28 degrees Celsius. You just reverse those two.
Right.
So you can use it that way. This is a weather map And the symbols that you usually would see on a weather map that have become familiar to many of us, the weather map that you see in the newspaper and the weather map that you see on television, the H is the center of a high pressure system, and the winds are blowing clockwise around the high. And if you continue on that movement of the clockwise rotation of the wind, many times you will create a cold front that is indicated in a line like this with the spikes on it. And of course, it isn't always as simple as that. You many have other variations in a stationary front on the one side where there is little movement of the air. The cold front theoretically will be moving down toward the bottom of the card. A warm front then is the rounded edge of the front along this side with the air movement up this way, and another cold front here, and a low pressure center designated by the L. But always there's a combination of frontal systems, and that means the variety in the weather that we have here in the upper Midwest.
Might be kind of interesting to point out these little vectors on here, that they usually are parallel to what you call these isobars, where there are lines of constant pressure, and the winds tend to blow parallel to those. So if you just see the isobars, you can often tell which way the wind's blowing.
Yes. And then if you could just make a cross-section of a frontal system. This is the warm front approaching us.
Right, the warm front then is this air. On this side, there's a cold bubble of air over on this side, and the warm front now is moving towards the colder air, so it tends to override it. And the warm front has been passing over places where there can be a lot of evaporation, raising the relative humidity, and as that air is pushed up, it cools, and as it cools, it reaches 100% humidity and starts raining. And then you can see these showers falling here, and this moves slowly, and the width of the precipitation band just moves right along with this, across like this. The various types of clouds are shown here.
The warm front that drags along the ground, and really the extension of it is some miles a distance.
Right. You can spot these things coming very often if you're over here where there's no sign of rain yet, and look up and see these cirrus clouds.
Those little plumes that shoot up.
Those little mare's tails.
Right. Well, then, an exact opposite, of course, is the cold front, and it approaches at a completely different angle to us.
The cold front is much steeper than the warm front, and it slopes the other way. And the other thing about this is the cold air now, and this is the warm air, and it's the cold air, of course, being more dense, pushes the warm air up, and since this is steeper, this rise of the air is much more rapid than it is with the warm front. And consequently, your more severe storms will occur with this kind of weather. You get these towering cumulus clouds, which develop the tornadoes and so on along the front.
You get the very sharp changes.
The very sharp changes,
with
that's right.
The cold front.
That's right.
Well, then another variety. And this illustration is really a combination of the two other fronts that we talked about, the warm front and the cold front, isn't it, Doctor?
That's right. We see really on here now, we see two bubbles of cold air involved. Here's the cold front, bubble of cold air moving in with its cold front. Here's the other bubble of cold air over here. And the warm air had been riding up over this. Now you've got the cold air coming in, pushing that warm air up, and we get the kind of occlusion. We've got the actions really of both kinds of fronts going on here. The fast rise due to the cold front, and then all this drizzle, and we usually get pretty miserable weather with this kind of a situation.
Can be some of the most serious weather too.
And it can be some of the most serious, yes.
So those are
Right there.
now, if it's a warm front or a cold front or a combination of the two, really the worst thing that can happen is a tornado. That's
right.
Here in our part of the country anyway. So we decided to create a tornado for you in the laboratory.
All right, I've got a kind of a model here of a tornado. The air is a fluid, water is a fluid, and the shears and so on in the fronts colliding give us rotation to the air, plus the air has some permanent rotation. But let me just get the air rotating fast, and we form what we call a vortex. And now, in our vortex, now maybe we can, I'll put some Alka-Seltzer in the water, and what one sees then is there's a pressure drop towards the center here, and all the little bubbles now you see collect to the center where the pressure is low.
Yes.
And you can see them whirling around in there in the vortex. There's a low pressure there. The bubbles are rising. You can see waves going up and down the vortex. And several things are displayed rather nicely, and the permanence of that little vortex. If you do that on a scale millions of times that size, you can imagine the amount of damage that it does.
Now, here's the story of how a tornado affected one community, and in particular, this young lady. Now, when conditions are right, the Weather Bureau deems it necessary, they will issue a tornado watch. Now, this is a preliminary to alert everybody to the possibility of a storm, and we'll try to outline the area where they think the tornado might appear. Then, if there has been a verified tornado, we've spotted it, the police have spotted it, or the civil defense people, then the Weather Bureau, and only the Weather Bureau, would issue a tornado warning, indicating where the tornado had been, the direction of the movement of the storm, and probably would urge everybody to take cover.
When do they blow the horn?
That's the time when the civil defense sirens would be sounded, when there has been a tornado spotted, and we have a definite proof that there has been a tornado touchdown. Now, should you live in a trailer court, I think we would urge everybody to leave the trailer.
Right. Trailer's not a safe place.
Even though they've been tied down, to leave the trailer and go to an area that has been designated in the trailer court. Perhaps even the laundry would be
That's right.
a safer place to be. If you're at home, go to the basement, and we've been working on a very sturdy, heavy table today in the laboratory. Go to the basement, and probably the safest place, without maybe worrying about direction or place in the basement, would be to get under a heavy table.
That's right. This would be a real good table to be under.
And away from the windows, because in a storm, in a tornado, you're going to be worried about blowing glass, debris, stones, trees, sticks that might be picked up by the wind and blown through the windows. Also, there's a possibility in your home, too, of the house exploding outward.
That's right.
With the reduction of the pressure.
I think it's a safe rule to open a window, especially on the far side. You don't always know where the far side is, but I think it's reasonable to have a window or two open to relieve that pressure so the house doesn't explode.
Equalize the pressure of the inside of the house to the pressure of the outside of the house. That's like the demonstration of the can, isn't it?
Right.
So if you're home, go to the basement and get under a sturdy table would probably be first rule of thumb. If you're out in your car, Doctor, you use your common sense, of course, in all these instances, but if you're in your car, sometimes you can outrun the storm, can't you?
Right. The storm travels about 30 to 40 miles an hour, and if you have a place to go relative to the storm motion, I think that you could get away from it.
Yes.
But you can't always do that.
No,
you might be headed right for it or something.
But common sense will come to your help in many, many cases. Thank you very much, Dr. George Freier. We've been visiting with the doctor in the physics department at the University of Minnesota, talking about our changeable weather here in the upper Midwest. Thanks again.
Most welcome. Most welcome.
Okay.
This will be a simulation of the conditions necessary for the production of severe weather. You can now see the outline of the United States in its western and northern parameters and will now describe those conditions that are necessary for the production of severe weather. The very typical situation for severe weather production is a situation where we have had a high-pressure system that has moved to the northeast. It is now located near the southern Appalachians, and a wide sweep of moisture has crossed the Gulf of Mexico, moving northeastward towards eastern Texas, and this fetch of cool air is picking up moisture being generated by the warm Gulf waters. This moisture is actually energy, the energy that is later going to be used in the production of severe weather as it moves northeastwards towards our area in Minnesota. To the west, we have a low pressure system that during early morning had been crossing from the southwest to the northeast, approaching southwestern Minnesota. The moisture has arrived in its 12 to 18-hour transport from the Gulf of Mexico, and lifting is already beginning ahead of the low pressure system. Showers and thunderstorms had shown early development in afternoon, and because of the moisture or energy availability and the presence of the low pressure system moving east-northeastward across Minnesota, a watch box will have to be issued. The watch box is normally 240 miles in length and about 140 miles in width. This situation is compounded by a jet stream which is crossing the low pressure system across the central sections of Minnesota and moving up into northern portions of Wisconsin. This condition will be compounded as the extreme showers and thunderstorm development begins in early afternoon in the west end of the watch box, moves to mid portions of the watch box by mid and late afternoon, and by evening in that critical period between 4 and 8 o'clock, the development of possible tornadic activity over the extreme eastern sections of Minnesota and portions of Wisconsin. So recapping then, of course, very quickly, we have the moisture that has been available being pumped into the area, which is energy. The low pressure system is moving over as a catalyst to set off the activity. We have the jet stream that is coming in, and the placement of a watch box has now been issued for the area. And of course, how do we deal with this situation locally, this severe weather threat? Let me show you. This is the WSR 57 radar. WSR for Weather Search Radar, 57 for year of development, made by Raytheon Corporation. The main scope that we're looking here at this time can give us an indication of where severe activity is located. As the sweep of the actual signal is going out and intersecting with showers and thunderstorms or severe weather, we can make a determination of where the centroid of the strongest activity is located. This is a glass on which we can make these marks, and it superimposes over what is seen on the radar set itself. By taking a paper overlay, we can extract this from the scope. Laying this map on the central location, this gives a range out to 250 miles here from Minneapolis, and to the right 250 miles. The most accurate analysis, of course, will be within 125 miles, and in our simulation, this is where the activity is located, out at a range of about 180 miles at this point. We've made the actual traces of the severe activity approaching the Twin Cities area and can extract this from the scope itself. In the simulation, the same indication, or those three same areas of severe activity, is located in relation to the watch box we had previously described over the central and south central portions of Minnesota. The X indicates where Minneapolis-St. Paul is located. It is now 2 o'clock in the afternoon. Here is the corridor of severe weather approaching the Twin Cities area from the west to east, and the red area that we're seeing now is the extract, or the point at which the most severe activity is located. This is about 1 county wide for the strongest cell activity, and we know within 2 to 2.5 hours it's going to be into the Minneapolis-St. Paul metropolitan area. So you can see the corridor of severe weather can be easily traced as the activity increases through the afternoon and evening period, as it approaches the metropolitan area and crossing the watch box area. If warnings become necessary, and we can analyze the vertical development of this activity on this scope, and we can come here and measure the intensity on this scope, and if this meshes with everything that we determine that is a requirement for severe weather, then the warning will be issued. On the areas, or in the areas either side of the hot track or the mean corridor of severe weather, we will issue statements for adjoining counties. In this way, we can cut down the number of warnings that are necessary, yet effectively produce a warning system that's compatible for what we need for the protection of life.
Now that we're out of the bathroom and all that humidity, what are the tools, Doctor, that you need for measurement of humidity?
Well, one of the usual tools for measuring relative humidity is this sling psychrometer, which I have right here. What you'll notice, the way it's constructed is just two thermometers, which are identical to each other. And in the room here now, they'll both read the same temperature. They're reading about 25 degrees in this room right here. Now, if I would take and wet one of these here, this has a cloth around it so that we can put water on it. And now, as the water evaporates from here, it has to go into the room air. And we said that a dry room isn't holding, say at 50% humidity, it can pick up a lot more moisture. So it would have to evaporate from here and go into the room. And as it evaporates, it makes this wet bulb cool. And the more it evaporates, the more this cools. And of course, the drier the room is, the more it'll evaporate. So the more this temperature drops, we can tell how dry it is. Now, we really should see that this gets well ventilated. So the usual procedure then is to take this and whirl it like this for some time. And you keep whirling it until the temperature of the wet bulb doesn't drop anymore. And at that point, you read it. And then one has to go to some rather complicated cables, but even that little bit of whirling that we've done right there, you can see the temperatures drop.
There's a
some
difference
already,
between
yeah.
the two. Yes.
Difference between the two. And the more this drops, the drier the room is. If the room were completely saturated, this wouldn't drop at all. They would stay exactly the same because no more moisture could go into the room. Now, I have another device that's very much like that right here. This little fancier, and it's got the two thermometers on it, but I might be a little bit shaky when I whirl that one. So to make it more uniform, and if different observers are doing it, this one works. You simply wind it up. And there's a fan here on the top then that pulls the air.
Motor in here.
There's a wind-up motor in here. The air is driven out here. It's picked up at the bottom. And again, what we have to do is get the wet bulb thermometer over here, and this time I just put the water up on here like this. And now if we let this run a while, again, the wet bulb will drop, and the amount of dropping will be proportional to how dry the room is. So that's one way of doing it. Now, that's always kind of a clumsy operation, those things. For many homes and so on, if you want to know what the relative humidity is, you use what you call a hair hygrometer.
Yes.
And a hair hygrometer, if you look closely in here, you just see a hair strung from here down to here, around this little axis, and then it pulls this lever up and down. Now, the hair is got the characteristic of absorbing more or less water. When it absorbs a lot of water, it gets soggy and lets the thing go one way, and then when it gets dry, it goes the other way.
Pulls
So
it tighter.
so it pulls it tighter. Different hairs have different properties for doing this. Someone told me once that the hair of a Swede works better
the
for
best
this
kind.
purpose than anything else. I don't know if that's a true story or not. So this can just be read continuously then. Now, we've been talking about several different devices for measuring things, and we might just take a look at this now to show how everything is handled at once. And we like to record it. So here I've got a clock-driven drum around here with pins. And this bottom one now is a slightly evacuated bellows in here. It's an air pressure. We'll push down more or less and change the reading on this pin over here.
And you get a continuous reading.
And I get a
then.
continuous reading of
on
that
the drum.
thing. Yeah. And now here is the hairs. It's a set of hairs in this one. And again, they'll pick up more or less moisture and make this kink bigger or less. Well, I can't push it around very much. But again, that'll make the middle pin get. And then up at the top here is simply a bimetal strip, which expands with the temperature, and that records the temperature up here. So then one has the pressure, the relative humidity, and the temperature. And with those three values, you can tell an awful lot about your weather. In fact, that's what you do every evening.
Yes, right.
Is give us those figures, and we could do more calculating with them if we knew what to do.